Corwin, and he's going to tell us about the KPZ equation and universality.
Yep. And so this is the main theorem that I'll end up stating is based off of a paper called the probability distribution of the free energy of the continuum directed random polymer in 1+1 dimension. And this is with Gidi Amir and myself and Jeremy Crestel. Okay. So I'm going to start by just giving you a fundamental object. And you might ask, why is it fundamental? And I'll give you a lot of reasons in just a little while. But let me write down this object. So it's called the free energy of the continuum directed random polymer, which I'll write CDRP rather than writing it each time. So what it is, it's defined as the logarithm, this expectation over Brownian bridges, which start off at 0 and end at position x at time t, of the following kind of weird object. It's a Wick exponential of minus the integral through white noise of the Brownian motion. So this is a space-time white noise. Okay. So let me give you a picture. The picture is as follows. Here's time 0. Here's time t. Here's position 0, and here's position x. And then there's white noise here. Space-time white noise you should think of as totally uncorrelated Gaussian noise. Okay? And what happens is you send out Brownian bridges, and they eat up the white noise. And then you assign a Boltzmann factor based on how much white noise they've eaten up.
So you sort of integrate over the path.
So you integrate along the path through the white noise field. You think of the white noise as a potential that you're integrating. So to every path, there's an energy associated to it. This is just a Boltzmann factor. Now, of course, there are these dots, and I'll need to tell you what they are. But then you take the logarithm, and this is the free energy. Okay? Now, this is a kind of a continuum model of something which people have studied a lot, some people in this room, of directed random polymers. And in fact, I'm going to give you 5 ways of making sense of this continuum object in terms of very concrete objects. So the first way of making sense of this is what's called through a chaos series or chaos expansion. So let me just tell you the 5 ways first. So you can make sense of this through a Wiener chaos expansion. And that's one way of making sense of this Wick renormalized exponential. You can also make sense of it through stochastic PDEs. Okay. And this relates to the stochastic heat equation or to the KPZ equation or the stochastic Burgers equation. You can also do some spatial smoothing of the noise. There is a problem of integrating through white noise. It's a very rough field that you're trying to deal with, and Brownian motions are very rough themselves. And so if you just naively try to make sense of this, you're going to run into a problem. So you need some sort of scheme. And one of the schemes is that you could smooth the noise in space. Another way is you can actually smooth it or discretize this white noise field in space and time. And then you get a model which is called the directed, or the discrete directed polymer. And I'll go into this a fair amount. And the final thing, and this is a rather odd thing, is that you can actually approximate this object in terms of discrete growth models and discrete particle systems. So you have the final scheme is that of growth models and particle systems. All right, interacting particle systems, IPS. Okay. So we have here 5 schemes. Now I'm going to explain how they work. But the main goal of this talk is actually, it's not to just make sense of this. It's actually to calculate the distribution of this object. This is a random object. It's random because you haven't taken expectation over the white noise. It's a fundamental object because it's related to these 5 things, which I'll show you. And we're going to actually calculate the probability distribution of this object, an exact formula. OK. So one thing that you can do to make sense of this is you can Taylor expand the exponential, and then you run into an issue when you're trying to define these iterated integrals of a certain self-energy when you're trying to integrate at the same time. So there's a procedure by which you time order this exponential. So if you look at e to the f t of f, you can define it, and maybe I'll take this as my definition, as what you get by Taylor expanding. So forget about the logarithm. Taylor expand, you have 1 over n factors, but then order time in a symmetric way. So you have t1 up to tn ordered. You get rid of the 1 over n factor, and you just have what's called the Wiener-Ito chaos decomposition of this. So it's sum n equals 0 to infinity minus 1 to the n. That's just from the minus. And then you have integral over t1 up to tn less than or equal to t, and then integral over Rn of the following thing. So when you do this Taylor approximation, or this Taylor expansion, you end up sampling the Brownian bridge at each of the points that you have your Brownian bridge, and you end up sampling it at n different times and points. So what you need to do is you need to calculate the probability that you sampled it at those n different times and points. So you get the probability, the n-step probability distribution for a Brownian bridge started off at 0, that goes through t1 up to tn and ends at t, and starts at position 0, goes through position x1 up to xn, and ends at capital X. And then, then you have all of these white noise terms. Okay? And so you end up getting a stochastic Wiener-Ito integral in each of these terms. So Tn. So you can take this as a definition. This is well defined. You can check this is a well-defined integral, and you can check explicitly in L2 of white noise that this is a convergent object. Okay? Just a calculation. Now, so this was the case of 1. Now it turns out that, in fact, you can think of, if you just cut this series off at a given point, let's say you cut it off at n equals 1. Well, then what you're actually doing is you have an iterative scheme which is going to converge as n goes to infinity to this object here. Okay? So what we do is the following. This is what's going to relate us to stochastic PDEs. We'll define ZTX as, we'll multiply by the heat kernel. This is just the standard heat kernel, the Gaussian. And then this e to the exponential of ftx. Okay? Now, why did I multiply by that p? It's because I want to turn this into basically something that looks like a Feynman-Katz formula. Okay? So I get rid of the logarithm by exponentiating, and by multiplying by p, I get rid of the fact that I'm dealing with Brownian bridges. I'd rather not deal with Brownian bridge if I want to do Feynman-Katz. I should just think of having a Brownian motion and then a delta function as the initial condition. And then if I do that, then I see that what I really have is I have a Feynman-Katz formula for a space-time white noise potential. So that would imply, well, that this should be solving a certain PDE, a stochastic PDE with space-time white noise. And I'll tell you what it is in 1 second. But if you define Z like this, then you can easily read off from this chaos series that Z satisfies the following recurrence. So ZTX is equal to PTX plus the integral from 0 to t, integral R, of P t minus s x minus y ZS y. Sorry. WD ds dy. You can see that if you iterate this scheme, you just keep plugging z back into it, you would get exactly this formula. Okay? So it's a calculation. But now what is this? This is nothing but the mild form, or the integrated form, of the stochastic heat equation with multiplicative noise. So this is actually solving the following in differential form. It's solving dtz is equal to 1/2 the Laplacian of z minus z times space-time white noise. Okay? And this is a well-posed stochastic PDE. And we see it's exactly, up to this heat factor, it is the exponential of this continuum-directed random polymer.
In fact, it's even linear, right?
And it's linear. Yeah. Now, what is the initial data for this stochastic heat equation? So I'll write this as SHE. I always mean with multiplicative noise, space-time white noise. Well, the initial data, from this perspective, when t goes to 0, we want the free energy just to be 0. We're not going to get anything. We have a bunch of zeros. So e to the 0 is 1, and then as t goes to 0, what happens to the heat kernel? It becomes a delta function. So the initial data, for this stochastic heat equation, is given by delta function, the fundamental solution of the stochastic heat equation with multiplicative white noise is what we're interested in.
Is that expectation value anywhere?
No.
So
So
what is W?
W is space-time white noise. So it's the same thing as here. The different, right, because here we took an expectation, but only with respect to the Brownian bridge. So this was also a function of the white noise. Yeah. Okay. So this is the second object, the stochastic heat equation. Now, I can right here. It turns out that this is related to two other important equations people have studied for a long time. So if you define ht of x to be minus the logarithm of z, then h solves the following stochastic PDE. So it's again 1/2 Laplacian minus, it's now a nonlinear stochastic PDE. So it's the square of the gradient plus white noise. This is called the Kardar-Paresi-Zhang, or the KPZ stochastic PDE. As written, it's not a well-posed equation. It's written because of the nonlinearity. Because if you remove the nonlinearity, you see Holder continuity in space of less than 1/2, like Brownian motion, and then you don't quite know what to do with this. So in fact, this h, which we define here, is what we call the Hopf-Kohl solution to the KPZ equation. And this is the physically relevant solution. People have studied this KPZ equation in the physics literature since 1986, cited 2,000 times. This is the correct definition of this KPZ equation, okay, in terms of the stochastic heat equation. Now, why do people study this? The reason is that this is a continuum growth model. It's a continuum limit of growth models, and I'll say something. I'll say a lot more about that in part when I talk about the fifth section. But essentially, it's a model for growth models that have two properties. They have a smoothing component given by Laplacian here, and then they have a non-trivial slope dependence, but subject to a rotational invariance. And anything which is slope dependent and rotationally invariant to Taylor expansion looks like the square of the gradient. And then it's random, so it's white noise. This was proposed by KPZ, in 86 is when they proposed this equation. They didn't kind of think about these, it was in the physics literature, they didn't think about these issues of well-posedness. In any case, this is an important equation, and furthermore, you can take the derivative yet again, if you look at u, which is dx of h, this solves the stochastic Burgers equation. With a conservative noise, which is even weirder. It's given by the spatial derivative of white noise. Okay? But it's actually something people study in the context of turbulent systems. It's something people care about. It's a toy model, but it's still. OK, so what is the point? The point is that all of these objects that I've introduced so far are all, in essence, the same as this. Okay? And you can access it through either one. Now I'm going to, these are all kind of high-level abstractions. Now let me give you a slightly more concrete thing. So this is the spatial smoothing of noise. So I'll just put it next to here. So that was 2. So this is 3. Another way of making sense of this this equation here, or this object here, is to smooth the white noise in space. And then you can actually define an integral of Brownian motion through that. Because if the Brownian motion wiggles a little, you're all right. You're not going to have trouble. So what you do is you introduce a multiplier, or some sort of approximate delta function. So let's say h is an even function, area 1 compact support. And so then you define delta kappa to be something like kappa h kappa of x. I think that's right. I'm never good with these. Yeah, that's right. OK. And then from this, you smooth white noise by that kappa quantity. OK, so you smooth it by convolving it in space. So this is w tx. So you convolve in space. This is a spatial convolution with the space-time white noise. Okay. I don't know. It's whatever you need it to be to get high, right? OK. So this is just a spatial convolution. So it still is rough in time. So this still is a distribution in time. However, in space, it's a bona fide function. And then what you do is you try to do the same thing, but for the smooth version of the white noise. So you look at it, and you notice that, well, if you're smoothing it in noise, so you can really just look at so you look at log. You don't need these dots. You can just make sense of this. So it's the integral, this smooth thing. So t d of t. But in order for this to not blow up, well, you're dealing with an exponential martingale. So you need to subtract off the martingale factor. The martingale factor is given by the covariance of the function, okay, integrated through time. And what's the covariance? Well, the covariance of white noise with itself is infinity. But the covariance of this smooth white noise with itself is just given by some, what I'll call C kappa. It's just the convolution of delta with itself evaluated at 0. So it's something that's blowing up as kappa goes to, I don't know, as it gets tight, as kappa goes in the correct direction, I guess, to 0. So then but the point is you need to subtract off this ck term. Okay? So you get 1/2 the integral of ck from 0 to t. So it's just 1/2 of t times this ck. Okay? And then the fact of the matter is Bertini and Cancrini in the early 90s, they proved that for any of these h's, this object will, as kappa, I think is to 0, this will converge to the thing I've written there, the ft. It will converge to the solution to the stochastic heat equation in this same sort of way. Okay? So you can smooth in space, and all you need to do is remove this. It's like a self-energy term, is what they call it, self-energy renormalization. Okay? So this is this thing. Now, the fourth and the fifth, this is where it gets very important, because these are models. These are kind of very tangible, discrete models that people have studied a very long amount of time, and there's a lot of interesting solvability questions. And it turns out that this is underlying them as well, but in a very particular scaling. And this is where things get a little more. So let me tell you. This is 4. This discrete directed random polymer. Okay. So what is a random polymer? It's a measure on paths. And since we're directed paths, we're just thinking about them going in one direction, directed. We're only, as the second title says, we're only dealing in one spatial dimension throughout. Okay, so it's very important. So what we're looking at is we're looking at a path, which, well, if we wanted to discretize this Brownian bridge, there are lots of ways of discretizing a Brownian bridge. The simplest, of course, is just a nearest neighbor random walk. So we look at a nearest neighbor random walk. So you can go, like this. And you end up at time n at some position y. Okay? And this is what you call a directed path. So it's just a random walk path. Okay?
We're on a lattice now.
We're thinking of this as on a lattice. So each of these are lattice points that you're going through. It's directed because if you think about a non-directed polymer, it can kind of move around on itself. And here the idea is that you're looking at a two-dimensional polymer, but you're making it go in one dimension, oriented in one direction.
It can't come back.
So it can't come back on itself, which makes it much easier because it doesn't resample the randomness. So you have kind of pure independence. So now the model is very. What was that?
I don't understand the word polymer.
Oh, forget about the word polymer. It's a random walk through which is being sampled according to a potential, which I'm going to explain now. So the potential is that for every lattice point, you have a random variable, wij, so each of these lattice points, and every other lattice point for that matter. And what you do is you do the exact same thing. You integrate the potential along the path. So you define a t of pi. So pi is going to represent my path, pi for path. T of pi is going to be the sum along the path, so ij in pi, of these random variables. So okay, so this is like an energy, or you can think of it, if you want, as a negative energy, depending on what you're interested in. And now, again, based on this sampled energy, you assign a probability. Okay, you assign a free energy, and what you do is you assign the probability of a given path. And let's let the initial point also be at time n, time m, height x. So we can go from 2 points from it. Mx to ny. So the probability at an inverse temperature beta, starting mx, going to ny. This is a probability measure on a path pi, and it's given by a normalization, which depends also on these two factors, times exponential of beta times t of pi. So it's totally analogous to this thing I said before. What you do is you assign an energy. If you think of minus the w's as energy, then this is negative the energy along the path, times beta. Beta represents a term, inverse temperature. And then you need to normalize. As beta goes to infinity, of course, you're going to just collect on the longest path. Okay? And
The most weight, right?
the path with the most weight. Of course, they all have the same kind of conventional length. Now, this z term is the partition function for this polymer, and well, logarithm of it is the free energy. So let me tell you exactly what z is. So z beta mx and y. This is just the sum over all paths. So I'll say pi in capital Pi mx and y. Capital Pi mx and y. This is just the set of all random walk paths from mx to ny. Okay. So I just kind of take, I sum over all possible paths, and then I just take this exponential of the t of pi. So this is just the normalization constant. Okay. But of course, it's random, because the weights are random. And I'm just averaging over the path measure, or the flat path measure.
So do I assume the weights are, at the moment, I can assume that they're sort of independent at each side, or?
For that matter, you can think of them as anything, but you should think of them as IID, because that's what I'm going to be dealing with.
But if you want to have analog of what knows what is the W?
It turns out that it's universal. It doesn't matter. So this is the approximation result that I'm going to tell you now. So if you want to get from here to this continuum free energy, well, what you need to do is first you need to recognize the stochastic heat equation sitting around somewhere here, because we want to prove convergence to this stochastic heat equation. Z is like a stochastic heat equation. In fact, what you should do is you should actually rescale a little bit. So take z beta tilde. We'll just take m and x to be 0. I note this. You can do general m and x, because once you know the partition function, you can actually, by using it, you can recover the probability distribution. But you take the product of the partition function, 2 partitions divided by 1 gives you the probability of going through a site in the middle. And this same thing actually holds. You can create a partition polymer measure for the continuum. So if I define this ny to be 1 over the number of steps, so 2 to the n, z beta 0, 0, and y. Okay. Then this z beta satisfies a very simple recursion relation, right? If you think about it, if you're looking at it at time n position y, it should only depend on its 2 neighbors back in time. Okay, there's a nice recursion. And in particular, the recursion is that it's equal to 1/2 the sum of its two previous time neighbors. So n minus 1, y minus 1, and n minus 1, y plus 1, times, I'll write it as 1 plus beta wij tilde. Here, what I've done, I've introduced just a new random variable, which is equal to e to the beta. This term here can be written alternatively as the product over I and j of e to the beta wij. And you can write as 1 and beta, some other random variable. Okay. So it's just convenient because now you see that if you just look at the term with the 1, you're just getting basically a Laplacian. And then the term with the beta is just giving you a noise term. Okay. So this is a bona fide discrete version of the stochastic heat equation. And if we want to converge to the stochastic heat equation, we need 2 things. We need to first rescale space and time in the way that the usual heat equation converges to the usual discrete stochastic heat. The discrete heat equation converges to the real one, which is diffusive scaling. And then the second thing is we need to understand how beta needs to scale in order for the white noise field, which we have here, to converge to space-time white noise. Okay, because these Wij's, they represent a discretization of space-time white noise. So let's see. Let me move over here. So it turns out that if you let's take n equals to, I'm going to use a parameter epsilon for a lot. It will be just a small parameter. So epsilon to the minus 4 times t, y, epsilon to the minus 2 times x. This is just diffusive scaling. T and x are kind of continuum time and space variables. And then the point is beta should be taken like epsilon times some fixed parameter alpha. This is the scale. If you take beta to 0, of course, if you don't take beta to 0, you're scaling space and time inward, but not rescaling the noise, so the noise will blow up. If you take beta going small, this is the way you need to do it in order for that white noise field to converge weakly to the white noise, space-time white noise. Okay? Then you have the following result, and this is an observation of Alberts, Kahana, and Castell. It's a work in progress to actually write it up totally rigorously, but subject to some moment conditions on these Wij's, you have the following universality result, which is that z tilde beta and y with these normalizations converges as a process to the solution to the stochastic heat equation with alpha sitting here. Okay? So this thing can also, so this is ZTX, which by rescaling is just alpha to the 4t alpha squared x, where z solves the continuum stochastic heat equation. So the point is that it is only under weak noise, when you scale the noise to 0, or equivalently beta to 0, or temperature to infinity, that you see the KPZ, that you see the stochastic heat equation, and hence the continuum directed random polymer. It's at that point. Okay? And this is something that one doesn't necessarily immediately realize in this case. Now, it's a function of a fixed discrete white noise, and then we're looking at a distributional limit of this function. So it's a space-time process, and as its distribution on a certain space of evolutions converges to the distribution of the stochastic heat equation with delta. I should remark with delta function initial data. So with this is the result. Okay, now let me just, in words, say something about the fifth one, because this is one I'll actually spend more time about later. The fifth one is the hardest. You don't see a priori why a growth model should have anything to do with this thing, or why it should have anything to do with the stochastic heat equation. And, well, it's hard. It's hard. And, in fact, there's only one example where we can prove this rigorously. And I'll tell you about that one in a little while. But it's important because the real question that we're going to be interested in, of course, there's the question of universality, trying to prove universality, for instance, in this setting. But the real question we're interested in now is studying the probability distribution of this continuum object, because that's then going to tell you something about the probability distribution about all of these things, these 5 things. For instance, if you know something about the probability distribution of that f, you know something about the probability distribution under the scalings I gave you of this continuum direct random polymer for a universal choice of these Wij's. Okay, so let me.
Those W could be independent, or what?
Yeah, so we can take them to be independent. You could have very, very short scale noise correlation, and it still would be all right. But yeah, you want them to be roughly independent. Okay. So the main point of the rest of the talk is to understand the probability distribution for this free energy. But let me just quickly.
So you're going to tell us what this actual distribution.
I'll tell you the actual distribution function. But before I do that, I want to entertain you with one question, which is, if I have time in the end, I'll answer, but otherwise we can talk about it. So this object here, this ftx, this is something which occurs only for weak noise. But what is the scaling limit for positive beta of this polymer measure? For instance, to make it very concrete, I'll introduce last passage percolation in a moment, but it should correspond to what you get by taking t to infinity, because we see that alpha and t play a similar role here. Taking alpha large is like taking t large, but alpha plays the role also of kind of moving you towards stronger weak noise. So what you get by taking alpha to infinity is almost like you didn't have weak noise at all. It's almost as if you had a positive beta. So my question is, what is the renormalization fixed point of the KPZ equation, or of this polymer free energy? To say it concretely, if I take epsilon, and then, well, I could do it in terms of f or in terms of the KPZ equation. Let's do it in terms of the KPZ. If I take the following rescalings, maybe I subtract something off, and I take epsilon to 0. This is a stochastic PDE. I'm rescaling it, and this is the correct rescaling. This is the KPZ scaling. What is the object you get here? As a space-time process. It's not, we don't know it as a stochastic PDE. In fact, we don't have any description of it. Well, okay, actually, so Jeremy Questel and I have a description of it at the level of physics now. And I can explain about this later, but just wanted to throw that out there as something to think about if you get bored with anything else. So this is a long time rescaling. This is the fixed point of the KPZ as t goes to infinity. You could also ask what happens when you take a short time limit of the KPZ equation. And then there is another fixed point, another renormalization fixed point, and it's given by the Edwards-Wilkinson universality class, which is governed by just the additive heat equation. It's what you do by taking the KPZ equation and removing the nonlinearity. Okay? But it's a big, there's some mystery still about what happens when you take the KPZ fixed point. This should be the fixed point which you get from this polymer model for positive beta. Now, some stuff is known about it. For instance, the spatial process is known. So let me define for you last passage percolation. Last passage percolation, it's the same thing as you get over here, but it's when beta equals infinity. So when beta equals infinity, you just pick out the longest path. Okay? And so if you look at the free energy, which is log of the polymer, of the partition function divided by beta, if I take log of this discrete polymer, beta of, this is the discrete thing, ny. If I divide that by beta and I take beta to infinity, then I converge to a statistic which lny is just the max overall paths from 0, 0 to ny of the passage times t of pi. Okay? This is the last passage time. This is the beta equals infinity version of these polymers. And in this setting, you can ask a very concrete question, which is, I look at n. So I choose n to be like, so I look at epsilon to the minus 3t, epsilon to the minus 2x. I subtract off some term that should, I guess, scale with epsilon to the minus 3. Divide through by epsilon to the minus 1. This is the same question as I'm asking here, but in terms of last passage percolation. The question is, what does this converge to? This spatial process has been solved. If you fix t, then you know what it converges to as a process in x. It's called the Airy-2 process. This is work of, well, for the one-point distribution, Johansen, Bike-Dyfed, and Johansen, and then for the process, it's Prahofer and Spahn. But the point is that this converges to a process which for a fixed t is stationary in x and is given in terms of this Airy-2 process. The marginals are given by the GUE, the Tracy-Whittem FGUE distribution, which for later purpose can be written as a Fredholm determinant, I minus, it's called K Airy on a L2 space S infinity. So we'll see some stuff like this in just a moment. So now we're ready. I've digressed for a little while. Now we're ready to see the main theorem. Okay? So we know that we should be looking for the probability distribution of this object ftx. So we have the following theorem, and this is like I said, this is Gideon Mir, myself, and Jeremy Costell of last year. And it says that if you define ft of s to equal the probability that ftx, it's convenient to put a t over 24, so let's turn equal to s. This is what we call the crossover distribution. This is equivalently the probability distribution for the KPZ equation, or for the log of the stochastic heat equation, multiplicative noise. We give the following formula. So ft of s is, we prove this, it's equal to the integral, contour integral over a contour which kind of goes around the positive real axis, e to the minus mu over mu d mu, and then a Fredholm determinant. And this Fredholm determinant depends on t and mu, and it acts on an L2 space kappa t to the minus 1 a infinity. Okay. So I should tell you, so a is just s minus log root 2 pi t. This just comes from the heat kernel term. Kappa is 2 to the minus 1/3, t to the 1/3. The point is that kappa is scaling like t to the 1/3. Okay? And this Fredholm determinant, this kernel, is given, is a general form, k sigma x, is given by integral minus infinity to infinity, sigma of t Airy x plus t Airy y plus t. This is a spectral projection with this sort of multiplication of the projector, and in our case, sigma t mu is just mu over mu minus e to the kappa t t. Okay. This is an explicit formula for the probability distribution of this continuum object. Let me just make sure. Yep. Okay. And we call it the crossover distribution. It's not a surprise that it's written in terms of Fredholm determinant, since when you take t to infinity, you should get the Tracy-Whittem, the GUE distribution anyway. Let me state a few corollaries of this result. So the first corollary, and this was of course people were interested in this for quite a while, but the question people really wanted to know mathematically rigorously was whether the KPZ equation scales like the KPZ universality class. So does the KPZ equation have t to the 1/3 variance, or I'm sorry, t to the 1/3 fluctuations as t goes to infinity. And so as a corollary of this formula, you have that exactly that result, which is that if you take t to infinity and you look in a scale of t to the 1/3, then this rescales to the Tracy-Whittem GUE distribution. So what this is saying, let's say in terms of this discrete polymer, is that when you take beta like epsilon alpha, you converge to this object, this free energy. This thing has this formula, this exact formula, and then when you take alpha back to infinity, which is like moving back towards having positive beta, well, then that's like taking t to infinity. And you see exactly that you recover the GUE. And in this way, you actually you prove a double scaling limit version of the universality conjecture, which I stated for the partition function, or the free energy of the discrete directed random polymer. Okay? Another corollary is that if you look at the short time, so this represents KPZ universality class scaling. If you look at the short time and you rescale it like t to the 1/4, take t to 0, then you just get Gaussian statistics. This is what I would call the Edwards-Wilkinson universality class. So this is really, you're sitting between two universality classes. And like I said, you also have this weak universality of the polymer. So let's say also you have a double scaling limit, a limit universality of polymer. So let me make a few remarks about this before I tell you how to prove it.
You can say something about what the paths look like and their fluctuations. So I think that's very,
right. So
very intuitive, and you haven't described it so far. So
well, so if you want to define the path measure for this continuum polymer, so you would define it in terms of the stochastic heat equation. Right. Of course, at this point. No, so we know what it should scale like. As t goes to infinity, the path should oscillate like t to the 2/3. Yeah. But we can't prove that yet.
Something about that, 'cause I think that's quite. I mean,
oh yeah, sure. So
we know that in certain cases. Certainly.
So right, so there's the point is that if you look at, let's say, the last passage percolation, or you look at any of these polymer positive temperature polymer models, and you look to some large distance t, the question is what does this kind of standard path look like? Okay? And the fact is that it lives transversally in a region of t to the 2/3. So it's not going to go much outside of a region of t to the 2/3 times a large constant. Okay? And we should,
It fluctuates much more than a
it will fluctuate much more than a standard, because it will go out and find.
It tries to find the environments which are favorable. Right?
Exactly. Yeah. So this is what's called superdiffusivity of the polymer, and this is related to the fact that the fluctuations of the free energy are actually less than what you expect from a usual Gaussian random variable or a usual central limit theorem.
But then the connection between the fluctuations in the energy and the fluctuations in X are the same as for one is just the square of the other, right? So it's the same as you have for ordinary random walk.
Well, if it's actually the relationship is supposed to be that 2 times the transversal fluctuations minus 1 is supposed to equal the exponent of the free energy fluctions. This is called the KPZ relationship.
Okay.
Yeah.
So it's just an accident of it.
It's just well, okay, at least the argument, it's an intuitive argument that they give. So about this, so at the same time as we derived this, so we proved this formula, Sasimoto and Spohn, so Herbert Sasimoto and Tomohiro Spohn, also derived this formula. They did it in a non-rigorous heuristic way. They do it in the same approach, but there are a number of points where, in order to make it rigorous, you need to be very careful. And actually, I'll explain the proof and point out 2 of these points. it really, it has to do with the critical scaling that you're dealing with. The other thing is that just reflecting on this, it's the first example of a nonlinear stochastic PDE, this KPZ equation, for instance, for which we can actually write down a probability distribution. It's solvable. I don't know what, there isn't a great theory for nonlinear stochastic PDEs actually computing distributions, and well, here's one case. Okay.
Are there questions about the structure of the path which is still open or not?
Yeah. So of course one needs, when you actually want to define a path measure here, you need to do this procedure that I was mentioning of kind of taking products of the partition function and using this to define it. And so in this paper, Alberts, Kahan, and Castell, they look and do this. But there are some.
You can calculate the probability that the path
goes through a given point.
Goes through various points, right?
That's very simple. The probability it goes through a given point is it's the product of the partition of the stochastic heat equation from this point to this point, and then this point to this point, divided by the whole thing. And so then you just take a limit of this. So, but then
you know that they're continuous.
You know that they're continuous, but it turns out, in fact, and so I'm not writing this paper, but I talked to them, and I think that they show that that's not absolutely continuous. So it's singular with respect to a Brownian bridge measure, this polymer, which I guess makes sense. But okay, so how do we go about proving this? So let me give you the 3 steps, and then I will. Well, actually, okay. So let me just explain how to prove it briefly, and then I can sum up with some questions. So the first step is we need to do this number 5. We need a growth model which rigorously converges to the KPZ equation, or to the stochastic heat equation. And so this is step A. So this is rigorous convergence result. Okay. And this splits into. So here I need to tell you what the growth model that we're going to look at is. And this growth model is called, you could either call it the corner growth model or the asymmetric simple exclusion process. And so let me explain to you what it is. You start a wedge. So I'll think of this as sitting above the axis. You start with an infinite wedge, and now you're going to grow out of this wedge. And the way that you grow is as follows. It's that there are 2 growth things that can occur. One is that every time that you have a local minimum, for instance, you have a single local minimum here, you can, at rate, so after exponential time of rate q, you can turn that local minimum into a local maximum. So you can fill it in. Okay? So in this case, you can only grow, and you'll grow after rate q. So this is a continuous time Markov process. But simultaneously, any time that you have a maximum, you will remove it. You'll die at rate p. So this thing, what was there, will go back and become a local minimum. So you kind of have this simultaneous growth and death of adding blocks and removing blocks. You can think of these as blocks. Okay? Now this can be coupled to a particle system in a very simple way. Everywhere that you have so you kind of put a half integer lattice, and above every site you look at the slope. And if there's a +1 slope, you put a particle. And if there's a -1 slope, you put a hole. So initially, this initial geometry is just a bunch of holes and a bunch of particles. And these growth rules are simply saying that particles try to articulate simple random walks, continuous time random walks. They try to jump to the left with rate q and to the right with rate p. And they do so only if there isn't a particle in the location you try to jump to. So for instance, this setup of a hole and then a particle, well, when the particle jumps, you're going to invert, so you'll have a +1 and then a -1. That's like growing a box. And likewise, if the particle then moved backwards, you would remove the box. So this is a coupling between these particle systems. The particle system is just the derivative. Okay. Now, question is, how is this related to the KPZ, to the stochastic heat equation? And for that, remember there was this idea of the KPZ equation was the continuum limit of discrete growth models. So I need to tell you in what way that's actually true. What you do is you want to look at the height function of this. So the height function just records the height of this interface. So initially, the height is going to be, so at time 0, so it's ht of x, and I'm going to put a gamma in. What gamma represents is the difference between q and p. Okay? So it's the drift. I'll take gamma to be between 0 and 1. Okay? So there's a net positive drift or 0 drift. So if I look at the height function of this system with asymmetry, or with q minus p equals gamma, then when t equals 0, this is just given by absolute value of x. Okay? And then I look at how this thing grows in time. Okay? Now, in order to get to the level, in order to prove convergence of the stochastic heat equation, I need to do something to get it like the stochastic heat equation. And we saw the KPZ equation was minus the log of the stochastic heat equation. So we should really reverse that. We should look at exponential of minus the height function fluctuations. Okay? But now the point is we need to understand how the height function itself fluctuates. Okay? Now this has been solved, so this is height function fluctuations. This has been solved, in fact, for the case of positive gamma. So Johansson proved for gamma equals 1, and then Tracy and Whittam proved that for positive gamma, we have the following result, which is that, well, if you have a smaller asymmetry, in order for all things to be equal, you need to speed up by the asymmetry. So if you had a slower drift, you need to run for longer. So you run like t over gamma. You look at position x. So here t is scaling like epsilon to the minus 3t. X is like epsilon to minus 2x. Okay? And I'll take fluctuations like epsilon to the minus 1. If I subtract off a law of large numbers term, which is just given by 1/2 t, and I divide through by t to the 1/3, then they prove that the probability that this is bigger than or equal to minus s converges to the FGUE distribution. Okay. So again, you see that this is converging to the statistics of this random matrix theory. It's converging to the same KPZ universality statistics. Okay. So now with this in mind, now we want to understand where does the KPZ equation come in. And, well, it's clearly not going to come in for positive gamma because everything's the same for positive gamma. There is a different thing that happens when gamma equals 0. When gamma equals 0, you don't have t to the 1/3 fluctuations. You're in a different universality class. You actually need to run, if you run for time t, you see fluctuations of the order t to the 1/4. So you have two universality classes, a t to the 1/3 and a t to the 1/4. And it's between them where you actually see the KPZ equation. So if you take gamma, which is scaling to 0 like epsilon, this is totally analogous to what we saw for the discrete directed polymer, where we took a weak form of the asymmetry. We took a weak noise. Here we take a weak asymmetry. And then under these scalings, we have the following result, which is that you look at h t over gamma x t, divide by the fluctuation scale, which we know is like epsilon to the, well, we can just write this as multiply by epsilon. Look at minus this, take exponential. This is the thing that should converge to something like the KPZ equation. But it turns out that in order to get the initial data right, we need to put in a prefactor of epsilon to the minus 1 over 2. This is what we call then z epsilon tx. Okay? And what we do is we prove, we have a theorem that says that z epsilon tx converges as a process to the solution to the stochastic heat equation with delta function initial data. So this is the fifth bit. This is one example of a growth model or interacting particle system which rigorously converges to the stochastic heat equation. In proving this, you actually, it's tricky because you want to look at the martingale that you get here. you want to look at the stochastic PD that you get for Z epsilon, and it just happens that for this nearest neighbor interaction, you can write this as a discrete version of the stochastic heat equation. For non-nearest neighbor interaction, you can't write it as that. It just doesn't work. This was an observation of Gartner in '88. And then Bertini and Giacomini, they dealt with a similar sort of situation, but not in this growth geometry. And it turns out in this wedge geometry, there's a different scaling, this epsilon to the -1 here. And you need to do a little bit of a different argument to prove this. So now once you've proved that your discrete model, your corner growth model, which I showed you here, once you've done A, now you have a path between this corner growth model, or this asymmetric exclusion, and the KPZ equation. And the next step is to actually say something exact about the corner growth or the asymmetric exclusion process. And this is, so Tracy and Whittam, they proved an exact formula for the probability distribution of the location of a given particle in the asymmetric exclusion process. So the probability that if you look at the location, so this will represent the location at time t over gamma of particle m, so this is less than or equal to some value x, they give an explicit formula. It's a very complicated formula. I don't have time to write it down, unfortunately. But what you can then do, and this is the third part, so this is part B, this is the solvability. The third part, C, I would say, is to then you take the scalings, which I showed you here, and you translate it into the parameters of the Tracy-Whittam formula, and then you take rigorous asymptotics. And let me just mention that there are lots of issues in taking these rigorous asymptotics. It turns out there's a very critical issue, which is that since epsilon is going to 0, you're in a critical scaling regime, and you end up doing a steepest descent analysis. And you have two contours, essentially, that you're trying to do steepest descent on. They're forced, they kind of are sitting very close to each other. They, in fact, are forced, this is like x and y. You're forcing that y over x is basically between 1 and 1 plus epsilon. But the fact is that there's a steepest descent point, and you want a given function, c, on one of the curves to be going to infinity, and on the other curve to be going to minus infinity, in the vicinity of this, some steepest descent point. Now, naively, what you would do is you would just say, oh, well, I'll just, C looks locally like a cubic. So if I want one to go to infinity and one to go to minus infinity, all I need to do is kind of deform it like this and deform it like this. But the distance now becomes order 1. And you can't deform anything past epsilon. So you basically are looking for two contours that stay arbitrarily, extremely close to each other, yet along which the same function has two extreme values. So you're basically looking for a cliff. And it turns out that there's one really needs to take this into account. Otherwise, it's just so this is one critical point in making this all rigorous. In any case, when you do all of this, you can heuristically at least guess the formula, and then if you do all of this sort of stuff, you get this exact formula. There are now there seem to be two other approaches towards exact solvability of this. One is through the replica trick, using the Lieb-Leiniger model with attractive Bose gas. And Dostenko and Klumov and Calabresi, Lidusal, and Rosso, they kind of developed a beta ansatz to analyze that model. They actually, so Dostenko and Klumov, they posted like a month before we posted, they posted an attempted solution, is what they called it, where they got the answer wrong, but they wrote down the beta ansatz correctly. They just, when you're doing these beta ansatz, you're trying to, you have these horrible divergent series and you're trying to resum when you do the replica trick, and you're going to get the wrong answer unless you know what you're looking for. So then they were able to actually recover the formula after the fact, once they knew the answer.
Once they knew your answer.
Yeah, but but actually it's still very useful because then you know the correct way to resum these series. And this replica trick, on a non-rigorous level, you can actually get a lot out of it. The third thing is there actually is some solvability for these finite temperature polymers. But let me just close with highlighting a few questions that still remain. So I've only talked about delta function initial data, or point-to-point polymers. There are other types of polymers people are interested in, line-to-point, for instance, or you could start out with a white noise on, rather than fixing the initial point, you could have some sort of potential on the initial condition where a potential for where you leave. And for each of these different types of situations, it's a very interesting question to understand the statistics. There is one case which we've also been able to solve, Jeremy and I. If you have white noise on half of the line and then minus infinity on the other half as a potential, we can actually compute the exact probability distribution. It's a crossover version. It's a kind of a crossover distribution version of what's called the BBP transition, the Bike-Benarus-Péchet transition, that occurs at the edge of the rarefaction fan in the exclusion process. So this is one question, to try to expand the solvability of one-point distributions. But you're also interested in understanding the multi-point distributions. I've just told you what ftx is at a single point. What about if you fix time and look at two spatial points? We should be able to calculate this. We don't exactly know how yet, but actually with these, there is some solvability which we think can be used to do that. What seems a lot harder is to calculate the multi-time distribution. And this is related to the fact that this is a Markov process in time. If you know the spatial process at time t, then you can get what it is at time t plus 1. But if you just know what it is, but that doesn't mean that you can project onto the value at x and the value at y at time t and t plus 1 and get a nice formula. And I actually don't think that there will be that nice of a formula there. I'm just guessing. So it's a big question. But then this kind of brings me back to this question of what the renormalization fixed point is anyway for this KPZ equation. Just to close, as an analogy, you can think of Brownian motion and the story of Brownian motion as an analogy to this story. The original proof of the central limit theorem of de Moivre, 200 years ago, it went through a solvable model. You took a simple symmetric random walk. You expressed probabilities in terms of Bernoulli random variables, binomial coefficients, and then you took asymptotics, and you get the Gaussian. And so in that very simple way, he was able to, from that solvable model, derive a property of a continuum object. Of course, then it kind of bifurcated. People proved convergence of lots of processes to Gaussian processes, to random, all sorts of random walks to Brownian motion. But people also developed a solvability, a stochastic calculus for understanding multi-point distributions and all sorts of different things about Brownian motion. Okay? And so then these two things combine to give you lots of information. We're at the point where clearly we have some universality. This is very much lacking, the universality of growth models and particle systems. But we've also accessed some of the solvability of this continuum object, and we've accessed it in the same way de Moivre did, through a solvable model. And perhaps we will develop in the future a better technique, a more robust technique, a functional sort of approach, but who knows? Hopefully it won't take 200 years. So thank you very much.
Thank you.